Good afternoon. This is the solution to bonus problem number 1, kinematics. And in this particular problem, we're going to be looking at projectile motion, in particular, projectile fired from a ship and trying to hit another ship which is hiding behind a mountain. And we need to calculate over what distance to the right side of the mountain a projectile cannot hit the surface of the water. In other words, over what range to the right-hand side of the shore of the island is this other ship protected? The angle of launch may be varied, as illustrated, between 0 degrees and 90 degrees. We need to show and discuss our working using our own handwriting and throw a drawing in as well. So we've got a few known values. Our velocity is 250 meters per second. The range from the ship firing the projectile to the peak of the mountain is 2,500 meters. The distance from the peak of the mountain to the easternmost side of the island is denoted as 300 meters, and the height of the peak is 1,800 meters. We've also got gravity as 9.8 meters per second squared. In order to get our velocity in our x direction, we're going to take our initial velocity and multiply that by the cosine of theta. And similar for our velocity in the y direction, we're going to take our initial velocity, which is 250 meters per second squared, and multiply that by sine theta. We're going to be using two equations to determine our x and y values. We've got delta x, which is velocity in the x direction multiplied by time, and delta y, which is our velocity in the y direction multiplied by time minus half g time squared. So x gives us our velocity multiplied by the cosine t. That's this one up here. And then for our t, because we haven't been given our time, we can rearrange this equation to give us distance x divided by initial velocity multiplied by the cosine theta. And I'm going to sub this value into t for our delta y equation just there. So that's this one here. We've got our velocity in the y direction multiplied by time minus half gravity multiplied by time squared. Neaten this up a bit and put our bits and pieces together, and what we can see from here is that we have a trig identity. So sine over cosine theta equals tan theta. So I've rearranged that one. And now what I'm going to do is split this half of the equation up, and that'll give us another trig identity. 1 over cosine squared theta is equal to tan squared theta plus 1. So what that has effectively done is taken our sine, cosine and cosine squared theta out of the equation and given us the same value of theta tan and tan squared. That's going to make it a lot easier for us to be able to work out what our angle is. Alright, so now from here I'm subbing in our values, our known values, into our equation. Y becomes 1,800 meters, x becomes 2,500 meters, our g is 9.8 meters per second squared, x again is 2,500 meters, this time it's been squared, and down the bottom we've got our velocity squared, which was 250 meters per second squared. I'm going to put all of our values onto the right hand side of our equal sign, so we've now got minus 1,800 in front of the original equation. And what I've also done is I've expanded these brackets, multiplied our gx squared by tan over our velocity squared. I've also multiplied that figure by 1 over our 2 times velocity squared. What that has given us is minus 490 rather. Rearrange this equation so that it's all working out nice and neatly. We've got tan theta 2,500 minus 490 tan squared theta minus 2,290. Rearrange that again so it's nice and neat, and this is what we end up with. this forms the basis of the quadratic equation. And for those who don't remember what that is, minus b plus or minus the square root of b squared minus 4ac all over 2a. I've used minus 490 for my a value, 2,500 for the b, and minus 2,290 for my c. Plug those values into our quadratic equation and we end up with two answers, a positive and a negative. For my positive, I've named that distance 1, and I ended up with, after the arctan of the 1.2, ended up with our lower value for our angle as 50.2 degrees, and the higher value using the negative sign gives us 75.7 degrees. And what I'm going to do with these two figures is I'm going to plug them into the equation that we already have for range, which is x, range in the x direction, which equals initial velocity squared multiplied by sine theta all over gravity. So for our 50.2 degrees, our distance 1, I ended up with a distance of 6,272.8 meters. And for the 75.7 degrees, our higher angle of elevation was 3,052.9 meters. So in order to answer the question, our original question, and find out what the safe area for the ship to be in and avoid being hit by the projectiles, I need to get my distances that I worked out earlier, and we need to minus that distance, or minus from that distance how far it is from the mountain peak to the eastern shores, which was 300 meters. I also need to minus the distance from the enemy ship to the mountain peak, which was 2,500 meters. So for distance 1, I ended up with 3,470 meters, and this is the furthest distance that the projectile can reach and clear the mountain at the same time at an angle of 50.2 degrees. And for distance 2, I ended up with 250 meters, and this is the closest distance that the projectile can reach the eastern side of the island, whilst also, once again, clearing the mountain. So to view that in a diagram, hopefully you can see it, this blue line here is our 75.7 degrees, goes up, over, just clears the mountain, not very drawn very well, and the safe zone is between the outer edge of the island and you've got 250 meters. So the ship can safely sit within that area and not get hit by the projectile. Conversely, this red line here, that is our angle of 50.2 degrees. That is the furthest the projectile can land while still clearing the mountain. Anything after that, the ship will be safe. So there we have it, projectile motion, making sure that the ship doesn't get hit by the projectile.